All right, now we're going to talk about naming with polyatomic ions. Okay, naming, and when I say naming, I mean naming and formula writing. And our polyatomic ions are our 21 for us that we're studying, are 21 collections of atoms that have a charge. Okay, so before we had something such as the chloride ion that looks like that, Cl minus 1. Well, now we have, I'm just picking one, hydroxide, which is OH minus 1. It's not a formula, okay? It's not a compound. It's an ion made of multiple atoms. So we have OH minus 1. All right, and how this actually works when we're trying to formula write or name. Let's pull up some example problems. All right. Well, let's just do it. Well, you have to be able to reference those 22 or 21, 21 polyatomic ions, their formula, their charge, their name at will. So I'm just going to randomly put stars next to a few. Okay, I'm going to start at the bottom one here because we talked about this on the last page. FROH, and I'm looking for the name. Okay, this big column is for the name. So I'm naming formulas. Okay, well, it's on your shoulders to be able to recognize that we're dealing with the OH polyatomic ion. Okay, that's why we're actually going through the trouble to actually memorize all those polyatomic ions. And I know that ion is hydroxide. Okay, so I have my polyatomic ion name. Now I'm going to deal with the cation, the positive end here. And Fr is francium. It's in the first column, so it's a +1 charge. We don't have to write a Roman numeral. And I just say francium. Francium hydroxide. And that's going to be true for all of these. Okay, if I look up here, I have KHCO3. Again, it's our responsibility to either go back to the chart or, better yet, have them memorized so we can recognize that there's a polyatomic ion in here, the HCO3. Okay, HCO3 is hydrogen carbonate. Hydrogen carbonate, and K stands for potassium. Okay, so we have potassium hydrogen carbonate. All right, potassium hydrogen carbonate. If I go down here to the other one that I put an asterisk next to, you have to be able to recognize that there's a polyatomic ion in here, ClO3, which is chlorate. And then Na is sodium. Doesn't need any Roman numerals or anything like that. All right, scrolling down. Now we're getting to the actual formula writing, which might be a little bit more difficult. Let's find out. Okay. Magnesium hydroxide. Okay, it's fitting that we're starting with hydroxide again. Well, if I know magnesium is Mg, and I know it's +2, I know that hydroxide, okay, the hydroxide ion is OH, and it's -1. Well, here's where I have to slow it down a little bit. Okay. And once you get good at this, you don't have to slow down. You can just write the answer. I have to rationalize this. Okay, I'm looking at my MgOH, and I know that it's not balanced. My lowest common multiple between my 2 and 1 is 2. I have to meet at 2. If I have to meet at 2, my magnesium is already at 2, but I am going to have to need, in order to meet at 2, I'm going to have to require two hydroxides. And in order to show two hydroxides, we write hydroxide, but because it's multiple atoms forming the ion, I can't write O2H2 or write OH twice. Okay, just like mathematics, okay, we have the parenthesis method and we put our little 2 underneath here. Okay, the subscript indicates that I have two OHs. And looking back, it makes sense. I have +2 and I have a -1 times 2. So I'm meeting at +2 -2 overall. Okay, and it's a very, very common mistake to try to alter, like I said, do something similar to this, MgOH. Oh, I need 2 of those. It's very easy to do something like that. And the quicker you get this through your head, the better. You cannot alter the polyatomic ion. Hydroxide is OH. Hydroxide is not O2H2. Okay, so you have to indicate that you have 2 individual OHs to go along with my magnesium. Okay, so you can't change the actual fabric of what actually we're dealing with. Let's do the peroxide down here, which is the oddball of the group, if I had to call one of them the oddball of the group. I have my lithium hydroxide, peroxide. I have my lithium as +1, and you're going to see why it's so bizarre. We have our peroxide, which is O2 -2. Okay, I want you to slow down and think about peroxide, O2 -2. That means each oxygen is -1. Okay, it's a little bizarre. Where am I going to meet? Where's my lowest common multiple? Well, I have a +1 and a -2, so I'm going to meet at 2. And when I meet at 2, I'm going to have, well, first of all, my O2 is already at 2. And my lithium, I'm going to need 2 lithiums to compensate. Okay, and that is my final answer. All right. It looks odd because it looks like you should reduce this to LiO. And the reason why you can't do that is because it's peroxide. Peroxide is O2. Just like when we were talking about the OH, you can't say O2H2. Okay, can't do that. You cannot alter the polyatomic ion of peroxide. So that means you have to leave your actual answer in the fashion of Li2O2. Okay, which is a little weird. Let's do this one. Aluminum dihydrogen phosphate. Okay, if I look up my aluminum, I know that it is plus, get my marker all set, it's +3. And dihydrogen phosphate, again, it really helps when we have all these memorized. Dihydrogen phosphate is H2PO4, and it's a -1. Okay, my lowest common multiple that I'm going to meet between 1 and 3 is actually at 3. Alright, so I have to get my compound to meet at 3 charge-wise in order to be equal and opposite to be neutral. So that means I only need 1 aluminum, and I'm going to need H2PO4, 3 H2PO4s in order to meet at -3. Each one of them is -1. 3 individual H2PO4s will be -3. Alright, so I'm neutral. I hope you appreciate we're really starting to get a higher atom count now. If I was going to count the total atoms in this aluminum dihydrogen phosphate, I would get 1 from the aluminum. You know what, actually, let's start with the dihydrogen phosphate. Dihydrogen phosphate is made out of 4, 5, 7 atoms. But I have 3 of them. Okay, so I have 21 total atoms from my H2PO4s plus my aluminum. So just taking a little time out here, appreciate that we're dealing with now a 22 atom compound. Okay, 22 atom compound. You know, we're really getting to some serious chemicals now compared to our binaries of NaCl, which was just 2. Now that we're dealing with 22 atoms in a compound. Okay, we're getting much, much more advanced. Okay, aluminum dihydrogen phosphate. I guess before I actually switch gears here to something just a tad harder, it doesn't really get much harder. I'm going to do this name down here. Okay, and I'm picking this one on purpose. Okay, because it's one of the stranger compounds we can have. NH4,2CO3. NH4,2CO3. What's so strange about it? Well, it's an ionic compound, but there's no metal involved. Okay, traditionally we have metals and nonmetals in our binary system. That's all we saw over and over and over again. And that holds true for our polyatomic ions in most cases. We have a metal with a polyatomic ion. Well, NH4 is our only positive polyatomic ion. So we have a position here where we actually have 2 polyatomic ions. And to actually name that, I have to know both polyatomic ions. NH4 is ammonium, and CO3 is carbonate. Ammonium carbonate. Number of atoms, I'm asking now, since we just did that with the 22, let's count them. I have NH4 has 1 plus 4 is 5, times 2 I have 10, 11 from the C, and then altogether 14 for my total ammonium carbonate. Okay, again, just goes to show that we've really progressed from our binary systems. We're really seeing a lot more atoms in our compounds. Alright, and this is about as hard as it gets. Okay, you can probably recognize when you're glancing over this sheet that you're dealing with the middle of the periodic table, the transition metals, okay, the unknown charges, the unknown ions, the multiple oxidation states, which stands for charges. Okay, so this is where we have to actually start worrying about our Roman numerals. All right, I'm going to start on the bottom. Okay, going from the actual name to the formula in the stock method of naming, okay, Roman numerals is the stock method of naming, is actually very, very, very easy. Okay, it's actually easier than before because they actually tell us what charges we're dealing with. Okay, for example, let's just start with the first one. I'm dealing with my lead 2 nitrate. Why is it easier? Because the Roman numeral says it's plus 2. I don't have to look that up. Okay, my life gets a little bit easier. I don't have to worry myself on what lead's charge is because it says it's lead 2, it's plus 2, it's done. Nitrate, of course, is NO3 minus 1. Helps to have that whole chart memorized of my polyatomic ions. And again, my lowest common multiple between 2 and 1 is at 2. So I'm going to meet at 2. In order to meet at 2, I'm going to have 2 nitrates. My lead's already at 2. So to have 2 nitrates, I would indicate my parentheses with a 2. PbNO3, 2. And I don't think I have to actually do many more of these. Lead 4 cyanide. Okay, we're back on lead. I probably should have picked a different one. It's plus 4 this time. Okay, it goes to show you that, you know, the multiple oxidation states of lead, Pb plus 2, Pb plus 4. Cyanide is Cn minus 1, meeting at lowest common multiple 4, PbCN4. Okay, not so bad. Like I said, these are actually easier than the previous examples we were doing. Okay, the Roman numerals and the stock method actually makes life a little bit easier. One more, and I'm going to do this one purposely. Copper 1 chlorite. Copper 1 means it's +1. Chlorite, and this is why I'm doing this one. We haven't mentioned the 8-ite, okay? I know that chlorate is ClO3, so ites are the same but with one less oxygen. So if ClO3 is chlorate, chlorite is ClO2, and the charge remains the same. Okay, I don't write my I do not write my parentheses. We're meeting at 1, we're at 1, so it's just CuClO2. I don't want to see the unwanted parentheses. Okay, it's totally not, you never indicate it that way. All right. So the stock method of naming, just like before, going from the actual name to the symbols, all right, I'm sorry, to the formula, it makes life actually easier. Now we actually have to think about going the opposite direction, figuring out charges in order to get the Roman numeral. Okay, what I mean by that, just picking one out of randomness. Let's pick this one. Okay, PbC2H3O22. Okay. First thing in my mental checklist is I know that Pb is in the middle of the periodic table, so at some point I have to figure out its charge. I also know that Pb is lead, and I also know that C2H3O2 is acetate. Okay. Well, we're on the right path here. The only hard part now is to find out what Roman numeral we're going to use. And the procedure for this is actually the same as it was before when we were doing binary namings. Okay, you have to know that acetate is -1. If acetate's -1, my overall charge here is -2. And because I only have one lead, that means my Pb must be +2. So it's lead 2 acetate. All right, another way to show that would be just to rewrite it C2H3O2. If I switch colors, that's what we have. Let's write what we should know. We should know there's an unwritten one there. We should know that that's -1. All right, and the question for the Roman numeral is to solve for x. Okay, equal and opposite, we have -2, which means this must be +2. What must x be? X must be +2. Okay, it's a very algebraic, very simpleton algebra, the way we actually look at it. Okay, and remember, x will always be 1 through 5, so we're not really doing calculator-based arithmetic. It's math that we can handle in our heads. Let's try to pick something as complicated as possible. Okay, so let's do this one. Sb2SO4 3. Okay, a lot of things going on here. Sb2, and you know what, let me do it down here. Sb2SO4 3. All right, and if I was going to write down, well, first of all, we should know that Sb stands for antimony. Antimony is in the middle of the periodic table. It's not in the first two columns or the diagonal of silver, zinc, and aluminum, which means it's a metal that needs the stock method of naming or Roman numerals. SO4 is sulfate. Okay, we have 3/4 of the work done. Ammonium sulfate. Can't say ammonium sulfate because ammonium is in the middle of the periodic table and it has different versions. So here's where we actually have to figure out what we're doing here with our antimony, figure out what its charge is. The unwritten information is SO4's charge is -2. Okay, and if I was going to do my math here, I know that I'm meeting here at -6, which means this must be by default, in order to be neutral, +6. What must x be in order to get, what is my variable x in order to get to positive 6? Well, it is a 3. Now some of us can spot patterns. You can say, oh wait, I can go backwards and figure this out. And it works in this case. It doesn't always work, so I would caution you to never try that. And let me see if we can figure out a method for that. Well, let's do this one. All right, FeCO3. Fe is iron. Okay, so we're going to do this one. FeCO3, we have my iron. Okay, and CO3 stands for carbonate. And iron being in the middle of the periodic table, we'll need the stock method of naming. So that means we have to figure out the charge. And FeCO3. Okay, what do we know about this? Well, if I switch colors here, my unwritten information is just a 1 there. And there's unwritten parentheses. There's a 1 there and a -2. Okay, that's my math. That's what I'm dealing with. Okay, I wrote all the unnecessary information in because it makes my life a little easier. Note that if you use this going up on a diagonal system, it doesn't work, because we'd say that iron would be 1 if we did that method of going upwards. That's why I say never ever do that. Never even try to look at it. Using my system of just rationalizing this, I have -2, which means by default this side must be +2. If this side is +2, my x must be 2. Okay, so x equals 2, so it's iron 2 carbonate. And that's just the gist of it. Okay, there's actually no way I can make it more difficult. That's as hard as it gets. I suppose it could be a little bit more difficult when you have a mix like this. And when you have a mix like these, when I say mix, basically we're dealing with metals that need the stock method and metals that do not need the stock method. And all you have to do is just slow it down and look up on the periodic table where these metals actually came from. Or hopefully we all have a little bit of familiarity with the periodic table that we don't even have to do that. For example, I'm just going to do the top 2. Okay, so we'll do these 2. SB stands for antimony, and it's up to you to know that antimony indeed needs the Roman numerals. PO4 stands for phosphate. Okay, so it's antimony phosphate, and since I have a -2 charge, I have a -3 charge, forgetting my polyatomic ions. Since I'm having a -3 charge on my phosphate, my antimony must be a +3. So there's my antimony phosphate. Now, I also have a phosphite in the next one. Again, there's the 8-ite rule showing up. And switching colors here, I have my lithium, but lithium does not need the Roman numerals, so I don't have to worry about the charge. Okay, lithium's charge is +1, but I don't have to say Roman numeral 1. I can just say lithium phosphite. Okay, 8 up at top here, antimony 3 phosphate. Now I have lithium phosphite. Okay, worst looking P ever. Again, the bottom portion here of the actual formula writing is pretty easy, because first of all, we know if we're dealing with the stock method or not, and the stock method in this case actually makes life easier. Okay, so for example, just to pick one, we'll do this one, and we'll do this one. Okay, mercury 2. Well, mercury is Hg and it's plus 2. How do I know it's plus 2? It says mercury 2. Chlorate, which is ClO3, and it's minus 2. Well, we have a lowest common multiple of 2. I'm eating at 2. I'm at 2. So it's just HgClO3. No parentheses needed, and do not write them. On the bottom here, let me switch colors just so we can see the difference. Okay, on the bottom, calcium hydrogen carbonate, and there is no Roman numeral. Since there is no Roman numeral, I have to look up calcium's charge. Hopefully I'm familiar with it by now. It's in the second column, so it's plus 2. Hydrogen carbonate is HCO3. Carbonate's minus 2, so hydrogen carbonate is minus 1. And my lowest common multiple now is 2, so if I have to meet at 2, I'm going to need 2 hydrogen carbonates. Okay, going a little too fast here. I see that I've talked for 26 minutes. So again, I need 2 hydrogen carbonates, so it's HCO3, 2. Okay, hopefully, and again, I'm meeting at 2, plus 2 and minus 2, so I have 2 HClO3s. Hopefully this was a worthy endeavor. If you're having any issues whatsoever with the use of polyatomic ions, it all starts with actually knowing the polyatomic ions. And if you know the polyatomic ions, life gets much, much, much easier. Okay, so hopefully when you're memorizing them with the flashcards or just picking them up by actually doing the problems, your life would definitely be easier from here on out.